Hi, welcome to this quick presentation about my project thesis that I'm doing at NTNU. My name is Juan Carlos Ayala Zabaleta, and I am studying a Master in Global Manufacturing Management, and I'm writing about a decision-making model for order picking technology selection in warehouses. So, yes, if you have any question or if you want to talk more about the topic, feel free to send me an email. And yeah, I can hold the presentation for you and go into more detail. So yeah, welcome. Yes, so to start with, what is the motivation for this study? And I have found mainly 4 points. The first one is that, of course, order picking is the most resource and time consuming process in a warehouse. There is enough research about it. There is enough knowledge about order picking, both in the practical side, but also in the academical side. So it is still relevant. It is still important and still needed to create more knowledge and to research this area, order picking in the warehouses. Then going more specific into the topic, selecting within the order picking, selecting the right order picking technology is an important thing for decision makers, managers, and so on, because it has implications not only in the financial side or in the strategic side, but also in the operational perspective. So this technology selection problem, it is a strategic and tactical decision that has really big impacts in the operation. Therefore, selecting the right technology becomes relevant. Further into this technology selection issue, the planned performance and the actual performance of the technologies can deviate if decisions regarding the humans, meaning the human factors and the well-being of the operators, are neglected. So sometimes most of the people implement something thinking only in the planned performance, but then when when the organizations have the machines, let's say the technologies on place, the actual performance is really different from the planned performance because there is an interface, and that was the humans, and the human factors were neglected. And the fourth motivation for this study is that selecting these technologies and implementing this technology is a complex decision-making process because there are many technologies and there are many criteria into this problem. So it's not only about the cost, it's not only about the performance, it's not only about the different technologies, it's how these criterias, these multiple criterias and multiple technologies correlate to each other. So it is important for the manager to compare these technologies before even having them, before pressing the button, before investing. So this study is focusing on something that is still not there, but that the companies and decision makers want there. So we need to understand what is happening. Then, in the order picking world, there is this really nice diagram from the Coster. We are focusing in here, in the system, in the method of picker to parts. This means that the picker, the operator, it can be a human or a robot, goes to the parts. Most of the warehouses in the world operate like this. Most of the warehouses, independently of the automation level, they operate within this area. So there are different types and different levels and so on, but we will be focusing on picker to parts. Let's say this is the scope of the order picking in the thesis. This the order picking system is in settings, which I like to call scenarios. It is a result of seeing how order picking in picker to parts happens. So it is divided basically into two. First, the multi-level, and second, the floor level. Within the multi-level, we have three sub-scenarios. First one is piece. So imagine a rack where the picker goes and only pick pieces. These pieces could be boxes, for example, medicine, or already prepackaged things. Then there are cases. Cases, imagine a rack where there are only cases. A case has a multiple units within it. And the last one would be a multi-level palette. For example, here in this picture, this area where I have the laser pointer, that is a multi-level palette. This, if someone manage to pick this, then this will be a multi-level case. And yeah, so multi-level literally means that there are many levels stacked into each other. It is usually within a rack. And then in the floor level, it is exactly as this picture. There is only the floor level in a warehouse. This might be used for bulky goods or for stuff that cannot be stacked into each other, or they don't fit into a rack. So for example, a forklift or a manual jack like this would go and pick the whole pallet, or an operator would go and pick one case. But this is only in the floor. So we will be assessing these 5 scenarios. Why are we assessing them in different? Because they might give a different technology assessment. They might give a different technology ranking. So fundamentally, they are different. Even though the operation, the order picking task operations are the same, the technology ranking might be different. This here I prepared a picture with the level of automation, starting from the basic one, the forklift. The forklift automates the travel, actually assists the travel of the operator. Then the scanner, pick by light, pick by voice, and head-mounted devices. These are paperless picking, so the paper is automated there. Then AGV and AMR, they automate a bit more the setup, the travel. The AMR automates the search. And then we have the PTR. PTR stands for Pick and Transport Robot, which it is actually divided into two. By the way how they pick the stuff, they could pick it to a bin, or they could pick it to a pallet directly. So this will be further divided into two. So manual order picking is here, and then fully automated order picking stands on the right side. So this is, let's say, the spectrum of order picking technologies. Later, here I present you the problem description. So I already told you the motivation for this study, but now the problem description. Up to right now, up to today, there is no academic research that consider the 3 main criteria, meaning productivity, quality, and well-being, to select an order picking within the picker to parts method. So this, in a way, hasn't been done before. Also, there isn't a study that considers the different system settings. Remember the different scenarios: multi-level case, multi-level piece, and multi-level palette, and floor-level case and floor-level palette. This hasn't been done, so this I think it is a problem. Also, selecting a suitable order picking technology is complex. Therefore, for the decision makers, the managers, it can be time consuming because it involves a lot of planning and a lot of investment. So there is also an opportunity to help and to understand a bit further. In this sense, this study tries to provide insight into this field, into order picking technology selection, while being of utility to practitioners. In this case, the decision makers would be managers, warehouse managers, logistics managers that work with this type of technology. What are the research objectives? There are basically 3 research objectives in this research. The first one is to develop a framework that helps the decision makers to understand the implications of order picking technologies, meaning how each technology is affected by each criteria, and that will be done via a sensitivity analysis. Then also we want to find the most appropriate picker to parts order picking technology, and and find and rank the technology suggestion, and this will be based on the weight of the criteria and subcriteria for each scenario. So this part will be done by it will be assessed by academic experts and vendor experts that know the technology, and this part, the weight of the criteria, will be done by operational experts, meaning managers and decision makers that have experience working with the criteria. Within this, within the weight of criteria, we also want to understand how the criteria and subcriteria affect each technology suggestion. And as I was telling before in the previous slide, there will be 3 relevant areas: the productivity, quality, and the well-being. The research methodology, it's here. So I will go really fast through it, but of course you can pause the video and see it in more detail, on better detail. But first, of course, we find the problem, then we will make a literature review on relevant topics, then we will collect data, we will analyze the data, we will do a sensitivity analysis, as I was telling, and of course we will interpret the findings and discuss and go to the conclusions. The workflow for this, so again, it starts with a problem definition, then I define the warehouse scenarios. These are the 5 warehouse scenarios. The criteria are defined by a literature review. The order picking technologies available in the picker to parts method also will be found or were found by a literature review. The hierarchy model for the Mcdm method were constructed by mixing the criteria and the order picking technologies. Then the data collection is done by a close-ended questionnaire with operational, academic, and vendor experts. Then, having all this, it will be used. The AHP, the analytic hierarchy process, will be performed with the software super decisions. And then, of course, after merging all the data and processing all the data, it will be interpreted and gone into a discussion and results and conclusions. So, what is AHP? AHP in this research is the method that will be used to assess the different technologies. AHP stands for Analytic Hierarchy Process. It is a method that has been around for years. It is really well researched. It is really well developed and understood mathematically, and yeah, it has been used in many different fields. One of the good things about AHP is that it allows linguistic data, qualitative data, and quantitative data. Therefore, here you can see different examples. Therefore, it is easy to have data from managers that might not have the data right away. They have the experience, but maybe they haven't been asked these questions, but the data is there. And with AHP, one of the good things about it is that we can still retrieve this information. Also, AHP allows input from many experts. It not only requires one, it can be used as a group MCDM. So yes, and it is based on pairwise comparisons. This last point is maybe one of the most important ones, and probably the main one that makes AHP such a powerful MCDM method, because this pairwise comparison, assessing directly one versus one and then assessing all the possible combination, gives a ranking. Of course, this ranking needs to be consistent. They must have some mathematical consistency. They should be valid. They should pass a test. But this pairwise comparison is really easy to understand. An example: if you are choosing a house, then you define what is important for you. Maybe the size of the house, the yard space, the price, the schools nearby, and so on. But you maybe don't know what is more important for you. Therefore, you will start to ask to yourself, okay, is the size more important than the yard space? Is the size more important than the price? Is the size more important than the location? And all these possible combinations, they will give you a ranking of what is more important for you, and ultimately will give you an answer for which house is better for you based on your own rankings. So that in broad terms, that is AHP. That's how it works. Here you can see the model of this scenario. So yeah, we will be assessing all the different possible combinations to find what is important and to find the order picking technology. I will go through this super quick. As I already said, AHP has been used in similar studies. It allows for the result aggregation, and we will be using the aggregation of individual judgments method within this method using the geometric mean method. This has been proved. This has been researched, and the geometric mean method keeps the matrix reciprocal. That's why it will be used. So, when it comes to the data collection will be divided in two. On one side, we have the operational experts. They will be answering direct pairwise comparisons. So they will be comparing productivity versus well-being, productivity versus quality, well-being versus quality, and then all the internal combinations to find what is the most important. Again, the aggregation method will be aggregation of individual judgments with the geometric mean method, and they will be using a 9-point scale. This 9-point scale is used and was defined by the creator of the method. So yeah, this is really straightforward. And then on the other side, to assess the technology, we will be requiring academic and vendor experts. These are experts with experience with the technologies and the capacities, and they will be answering a questionnaire that is based on the criteria here. So why did we divide it into two? First of all, because the operational experts, they are the ones having the direct experience with the criteria. They know what is important for the business. They know what is important for their daily operation. So that they have that experience, and it's their duty to deliver results based on this performance indicator. On the other hand, they might not have the experience on different robots, for example. They might only have experience with certain type of technology, so they are lacking this other side of this overview of the different possible technologies. And here, of course, the academic and vendors, they do have knowledge about the different technologies. They know what the technologies can do, but they might not have the practical experience that an operational expert, that a manager have. They know how to develop the technologies. They know what the technology can do. They are leading the research on these innovative technologies, and they are actually familiar with their capabilities, but they are the ones familiar with the criteria, and they know what is important for them. So by dividing this data collection into two, we will be having hopefully a valid approach to this problem. Here I am showing the order picking criteria. As I've been telling you, it's divided into three. Productivity. Within productivity, we have the costs of everything. It involves setup costs, like all the financial costs that could be there, maintenance, investment, and so on. The throughput, the utilization, and the cycle time. These are productivity metrics. Then we have quality metrics. Quality means damage to the product that could be done in the order picking process, and error. Error means all the possible failure modes that could happen within an order picking. Few examples could be picking the wrong thing, picking the wrong amount, picking late, for example, and all the possible errors that could happen in the process. And then this is the human factors, the well-being of the operator. And then we have a physical workload, how much physically is the operator working, the mental workload, how much is the operator thinking, the perception, how is the operator perceiving the task, the injury, this would be the risk of injury, meaning repetitive tasks and all these side, lifting and so on. So that is involved here. And then the psychosocial, how the operator is related to the work, the motivation, the stress, and so on. So ultimately, these are the three main factors, the three main criteria, and the sub-criteria that will be assessed. How this will happen, how the criteria will be happening. Here, this is how with the pairwise comparison. So we will be asking for you, manager, for you, operational expert, what is more important, performance or quality, and how much? Performance or well-being, and quality and well-being. If you see with attention, these are all the possible combinations that could be there. Within performance, for example, we will be asking what is important for you, cost or throughput, cost and utilization, and so on. So all the possible combinations. It might be the case that there might not be a number, but then it can be done linguistic, and that's one of the strengths of AHP. So these are alternatives for answering these questions. And then on the other side, how will we be assessing the order picking technologies? We will be using the academic and vendor experts. We will be having, again, this is the level of automation figure. And these are all the different order picking technologies. We start with picklist. Picklist, it's per se not a technology because paper, it's not a technology. But picklist is the most basic one, and it is still used in the world. So it might be that picklist, maybe it is better than a fully automated robot, or the other way around. Of course, they have different implications, and these different technologies play different roles within all these criteria. If you see here, something that is interesting for this research is that the alternatives are ranked versus criteria. They are not ranked technologies versus technologies, because that wouldn't be fair. Comparing a pick list versus a fully automated robot, it's not fair, because fundamentally they are completely different. Even a forklift or an AGV versus a fully automated robot, it's not the same, because they are automating and assisting the order picking task in different levels. Therefore, that's why it was decided to compare the alternatives versus the criteria. Then we are having the same common ground for them. And here I am presenting you the conceptual hierarchy model of the whole research. So we have the goal, that is finding, of course, the best, the most suitable technology, order picking technology. We have the second level, which are the criteria, and then we have the sub-criteria level, which are these. This cycle thing, this cycle here means that they will be assessed with inside. So we will be assessing the different combinations, and then we have the different technology levels. This is the base. This is the base of the hierarchy model. So pick list will be compared against all these, and all these, forklift again, and so on. So this is how AHP works. This is how AHP is constructed, and so on. So this is the core of this thesis, basically. What will we be delivering? Again, this is tied to the research objectives. We'll be delivering a framework backed up by relevant and valid literature for assessing order picking technologies against criteria. So we found the order picking technologies and we found the order picking criteria based on that. And then we will be constructing a framework to assess these two. We will give a suggestion for order picking based on this input. We will also give the relative weights for the performance criteria. Relative weight means what is more important, which criteria and sub-criteria is more important for the different scenarios. And all these will give information on what is more important between the technologies for a given criteria. So one technology might be preferred for one criteria or other technology. For example, a big example here. If cost is a big constraint, meaning it's a big important factor, then picking list, I am exaggerating, then picking list will be better ranked than a fully automated robot. On the other hand, if cost, let's say the wallet, it's not an issue, then a PTR might be a better option than a picking list, because you can spend money on that. Another example would be if you don't care about the physical workload of the operator, then maybe again a picking list might be better than a fully automated robot, because the fully automated robot does not imply any physical workload on the operator. So we will be, with the weights and with and how the weights and the technology correlate to each other, we will be having this point, what is more important between technologies for the given criteria, and ultimately I will be delivering a thesis. So yes, thank you. This was a super fast presentation. Again, if you are interested and if you want to know a bit more, or if you still have questions or you want to know a bit more in depth about this research, please don't hesitate to send me an email. And thank you again for your time.